There you go. So, hey viewers at home, you already missed some class. We're on page 46. So, here is, one of the things satellites can only tell you, though, is information about the surface. A satellite can't tell you anything about deep down in the water, because any light signals that it's getting, any radio signals or anything that are coming off the satellite can't go to any depth in the water. But here you see the red color, that's warmer water, and the blue color, that's colder water. So just looking at the coast of the United States, you see there California, that's got cold water there. That blue is cold. The coast of Georgia here, we got warm water. See? Has anyone here ever been to California and dove in? Yeah? Was it cold? Freezing. And that has to do partly with the circulation, which I'm going to get into next, which is very interesting. Did you wear a wetsuit?
No, but I also went swimming in the ocean in Alaska.
Oh, well, that's real cold.
Yeah.
That's even colder.
There's starfish.
Whoops. This is called a Secchi disc. Secchi is S-E-C-C-H-I. Secchi disc. And a Secchi disc, I have a Secchi disc right here. We'll bring it out tomorrow. You want to? Mine looks a little different from there. And it's just a white disc with a weight on it. And you lower it down into the water. Whoops. Now this has a line on it for each meter of depth. A meter is about 3.5 feet. So the kids drew, a long time ago, drew a black line on this for each meter. And anyway, you lower it down and you just wait until you can't see it anymore. And the distance that you can lower a Secchi disc and not see it anymore is called the Secchi depth. And that's a measurement of how clear the water is. If the water is real dirty, this thing's going to disappear rather quickly, and you'll only get down a few meters, a meter or two, and you won't be able to see it anymore. If the water's real clear, you can lower it down 20, 30, 40, 50 feet and still see it, maybe even 100 feet, depending on where you are. What do y'all think the water is here, clear or dirty?
Dirty.
Oh yeah? Why don't you make a hypothesis in your little book there, guessing how deep the Secchi depth will be tomorrow? How many meters? Huh? Do it right now. It doesn't matter, it's just a guess. We can just see who's closest.
What should we call the lab we're doing there?
It's going to be a water, it's on the syllabus, water measurement. Water quality testing. Thank you. Here, I'll pass around the Secchi disc. Here, have a Secchi. Don't say I never gave you a Secchi disc to look at. This one's colored white and black, but they can just be white. Gives you some contrast when you're looking at it there. We know this about the water after a lot of studies are done. Different colors of light can penetrate the water different distances. Remember, light that comes from the sun consists of all colors. Red, orange, yellow, green, blue, violet. Red and yellow and pink and green. Y'all remember that song? It was big in 2nd grade. Red doesn't get far through the water at all. Blue can penetrate the deepest. So when you're down deep and light is hitting something and bouncing off of that something and into your eyes, it'll look blue. Everything down there that deep looks blue. And here's a picture of a starfish down deep. And doesn't it look blue? That's just because blue penetrates real far in the water. Here it is when the guy's shining a light on it. The diver's shining a light on the same starfish. You can see it's actually red and white. But without his light that he's holding, the light from the sun won't get down that far. Isn't that interesting? So when you're diving down there in the oceans, you won't be seeing things their actual color unless you bring a light with you. Blue penetrates the farthest, and red penetrates the least. You probably should know about water pressure. And this is the most important thing for divers. Who here has a diving, is certified? Just Stephanie?
It's the number one rule to never hold your breath underwater.
I was going to say, they talk about this a lot. I took all the diving courses and did all the coursework, but I never did the actual diving.
Why?
I don't know. I was lazy. I need to get it done. But anyway, this guy in this boat has filled up a big balloon. I don't know why. Maybe it's his birthday. And then he's going to dive in, and he starts going down. And as you go down in the water, the pressure builds up. And basically, you can think about it like this. When this guy's down here 35 meters deep, it's like he's being pressed down by 30 meters of water over his head, pushing down on him. And it doesn't just push down on you, it pushes at you from all sides. That's the weird thing. So a balloon that was real big in the boat gets pushed on from all sides and becomes a lot smaller. And if you could go this deep, which you can't without a real heavy suit, which is why they show this alien-looking suit right here. Look, the balloon is just smashed into a very, very small, tiny space there.
When you come up, like when you're down deep and you come up, you have to go like 5 feet and stop for like 5 minutes. And then go 5 more feet and stop for like 5 minutes. So it takes like 30 minutes to get back to the surface.
Yeah, and
if you go too fast, your lungs will expand.
The air in your lungs will expand, and you got to give time for that air to escape. And they say if you go up at a certain speed, though, you can breathe out the whole time because the air is expanding. You can just breathe out for as long as you can right now. Imagine if you could keep doing that. You can keep breathing out the entire time as you're coming up from the bottom for minutes because that air in your lungs expands and expands and expands and will come out if you just breathe out. It must be an interesting sensation. Have you ever noticed that when you've come up from depth? No? So the expansion of air is a really important thing that you have to worry about. And you can see the pressure here. ATM means atmospheric pressure. And at water depth 0, you're at 1 atmospheric pressure. That's the pressure of the atmosphere pushing down on you. That's normal pressure at sea level. We call it 1 atmosphere. Or it can be measured in bars or PSIs, pounds per square inch. That PSI is an interesting measurement. If you took a square inch of skin or a square inch of area, which is an inch this way and an inch this way, so a square inch is about that big. At atmospheric pressure, it's like there's 14 pounds of pressure pushing on each square inch of surface. That's normal pressure. We're used to that. You don't even feel it. But if you go down 80 meters, now it's like there's 132 pounds of pressure on each square inch. That's a lot more. You can feel this when you go down in a pool. You can feel it in your ears. Have you ever felt that, the pressure? And so what you do is you equalize. You hold your nose and you push, and that pushes air up on the inside of your ears to counter the pressure that is going out. You have to do that when you're diving as well, right? Or you'll bust your eardrums. Hello. caught and pulled up from the bottom, and they pulled it up real fast, and the gas in its swim bladder expanded and is pushing the swim bladder out through his mouth. That's the swim bladder of the fish, which is normally in the middle of the fish.
Did it die?
Probably so, yeah. That's not a pleasant thing, probably, to have your swim bladder blow up inside you. Okay, the next thing I want to talk about is water circulation. The water on the planet doesn't just stay still. The ocean water is not just sitting there, it moves. And one of the main reasons for the movement of the ocean is called the Coriolis effect. Have you ever heard that before, the Coriolis effect? It has to do with the fact that the Earth is spinning. And the Earth spins like this. If you look at it from the North Pole, the Earth spins in a counterclockwise direction. Counterclockwise if looking from the North Pole. And because of the spinning of the Earth, and because the water can move, the water is turned a certain way as the Earth spins. You getting this, Nyoka? And the net effect is that anything that is moving in the northern hemisphere bends to the right. Anything that is moving in the northern hemisphere will bend to the right. So if you were on the North Pole and you shot a missile down towards Charleston, it would actually bend as the Earth turns, and it might hit San Diego if it was traveling at the right speed. You can think of it as the Earth is basically turned underneath the missile. And so the Earth is shifted that way while the missile is going, and so there's a curve. Notice it's a curve toward the right. And even if you launched it from the equator toward the North Pole, it would still turn to the right. And I know that's hard to understand and hard to fathom. I'll show you a little video that might help explain it. But if you've ever been on what are those kids' games? Not the big things that spin. You spin like you spin it around like this. What? Yeah, on the playground. You know what I'm talking about? What's that called?
Merry-go-round.
Not a merry-go. A merry-go-round has the horses and stuff on it, and those are fun too.
Oh wow! Hang on to it.
Yeah, you can hang on, and they can get you spinning. And
Yeah.
what is that called? I know it has a name. Trey, do you know what it's called?
Mm-hmm.
What?
No sir.
So anyway, if you stand in the middle of one of those, if you're ever on one of those, play this game. Stand in the very middle and get a ball. Surely I have a ball around here. Here's one. Get that thing spinning, first of all. Don't get it spinning too fast or you'll start throwing up. But anyway, you get it spinning and go stand in the very middle of it and then take a ball. And get it spinning counterclockwise just like the Earth does. Okay? And then roll the ball from the very center. And you'll see that it curves to the right. And then go to the edge and have a guy at the center and try and roll the ball to the guy at the center. And you'll see that it curves to the right. Whether you're from the outside or from the middle, if you try to roll the ball along this merry-go-round-like thing, it'll always curve to the right if the merry-go-round's going counterclockwise. And you have to just take my word for it. It's hard to explain. It's a physics thing. If you take physics, you'll study it in more detail. But everything curves to the right due to the Coriolis effect.
What about if you're in the southern hemisphere?
Everything curves to the left in the southern hemisphere. No matter which way you throw something, no matter what direction you're facing, everything will curve to the right in the northern hemisphere and the left in the southern hemisphere. You know that military snipers even have to take this into account when they're taking very long shots? A sniper knows if he's in the northern hemisphere and he's shooting from something like 800 yards. Now, okay, you're falling asleep talking about snipers. This is interesting. Trey, don't you want to be in the military?
Not really.
No. And you shoot that gun, because of the Coriolis effect, you're going to have to, if you're shooting from hundreds of yards away, you're going to have to correct about an inch, or maybe a little less than that, to one side for the turn because of the Coriolis effect. And they certainly have to correct for it on airplane flights and missile shots and things like that. So it's a very large effect. Oops, I wanted to show you this YouTube video. Up. Why isn't that? Well, I guess I can't show you.
Victory is mine!
See if I can find it just regular. I thought I had it on there. YouTube? Coriolis effect. Here we go. I think this is it. Uh-oh, this might not be it. See, turn to the right. There's no sound. They're having you spin with it. This is a physics thing. Okay. Oh, here we go.
To an observer above the merry-go-round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis Force, whereby to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
That was freaking awesome.
To an observer above the
Now, why is it turning to the left in this picture? Because it's what?
Speaking of a mirror,
Any idea?
it's going to the left.
Because they're not going counterclockwise, they're going clockwise. So that's like the southern hemisphere.
Go round, the path of the ball appears straight, while to someone sitting on it, the ball appears to curve to the left. This exemplifies the Coriolis Force, whereby to an observer on the rotating Earth, the path of an object appears to be deflected, and this is a result of the Earth's rotation.
We
Okay.
should go find one of those.
Yeah, when I went to the first football game last year, they had one out there, and so I got on it and I was playing on it because it was about the time I was teaching this. And all the kids on the other team thought I was something was wrong with me.
Wait.
Because I'm out there playing on this thing. I'm rolling things around.
Here?
No, it was at another school. They had one on their playground. And I was teaching this, and I was trying to check it out, you know, see if it was real. I didn't believe it.
Victory is mine!
Whoops. What is this? We already did this. Okay. So the Coriolis effect is one thing that really changes the movement of the water. But there's another thing. Wind. here's how wind works. Wind is due to rising and falling air. Now, Alka, stay with me here. When air gets hot, it rises. And then when air cools off, it falls. Okay? And so what's the hottest point of the globe? The equator. So what happens is the air gets real hot around the equator and rises up. And that's what these arrows show. And it rises up. Now, when the air rises up, something has to come in to take its place. Trey, will you pick your head up for me just a little bit? Thank you, sir. When the air rises up, something has to come in and take its place. So air blows in from the sides to take its place, you see. So the air rises up, air comes in to take its place, and now there's less air over here, so the air that's up here kind of falls back down and takes its place. And there's these currents of air that rise from the equator and fall to near, this is about 20 degrees latitude, and fall and then come back in. You have these air currents. And the air currents also push the water. And notice the currents are bent to the right in the northern hemisphere and they're bent to the left in the southern hemisphere. So these air currents play an important role in moving the water around. And so we have these winds that blow toward the equator and kind of at an angle due to the Coriolis effect. The ones near the equator are called the trade winds. Have you ever heard of that, the trade winds, before? It has to do with the trade routes that people used to run. They followed the trade winds and to get their sailboats to the right place. And then up in the more northern latitudes and southern latitudes, you have what's called the westerlies. Winds kind of blowing out of the west. And then up near the North Poles, you have the easterlies and the South Poles. And this is all due to the circulation, due to rising air and falling air that comes about. So when we put it all together, oh, there's one more thing. How does wind blow the water? Let me ask y'all a question, and it would seem like to be a very easy question, but it actually turns out to be difficult. If you blow on the water, let's say I have a body of water, a little pool of water here, and I'm blowing on it. Let's say I got a pool of water right here. Or let's say I'll get tired if I keep blowing like that and I just turn a fan that's blowing on the water. Which way do you think the water's going to go? What do you think it would go? This way?
Right.
If I'm blowing on the water from this side, don't you think it would go that way?
It would go right, but wouldn't it make...
It doesn't. It doesn't go that way. It actually goes this way. And the idea behind that is strange, but it has to do with the Coriolis effect. As the wind hits the surface of the water, the Coriolis effect in the northern hemisphere bends it to the right a bit. And so you see the surface current will go at a 45-degree angle to the wind direction due to the Coriolis effect. Remember, everything bends to the right. Drew, you with me? And so the wind's blowing this way, and the water's going at a kind of an angle. If you go down further, deeper in the water, this water that's going this way influences the water below it to go that way, but even further to the right. And so it's just like the wind blowing at the top, the water below that goes a little to the right, the water below that goes even more to the right. And you get more to the right the further down you go. And real deep, the water is actually going in the opposite direction of the wind. because of the Coriolis effect, continually turning the current to the right.
Can the current be stronger under the deeper you go?
It's usually not.
Can it?
It can be if the current is not due to the wind. The current can be due to other things beside the wind, which we'll get to. I don't know if we'll get to it today. Anyway, if you add together all these arrows, the resultant transport is at a 90-degree angle to the wind direction. Trey, if you were in the southern hemisphere and the wind was blowing this way, where do you think the net transport of the water would be going? This way? That way? This way? Nope. Anyone have a guess?
Wait, what was the question?
If you're in the southern hemisphere and the wind was blowing across the water this way, what would the net transport direction of the water be?
The opposite?
It would be to the left. The northern hemisphere, everything kind of turns to the right, but the southern hemisphere, everything kind of turns to the left. So you get net transport in a 90-degree angle to the wind direction, depending on the hemisphere that you're in. So here's what we end up with. All kinds of different currents, depending on where you are in the world. Let's look at our currents up here. Because of the winds and because of the Coriolis effect, remember, our currents will go to the right. So we have a big current that comes by our land, where we are. There's us right there. Yay! St. Simon's. Woo! And the Gulf Stream is going by. And it actually comes up and brings water from the Caribbean. From the Caribbean down here. And pulls it up. And that's hot water because it's near the equator. There's the equator. And that water is real hot, so it's brought up and it curves to the right and it curves around like this. And by the time it gets up here to England, it's starting to cool somewhat. So England has cooler water than we do. But even England has water that's come up from warmer areas. Go to California, it's totally different. The water has come up from here and is hot and now cools off and comes down. Hey, be ready to go do some water testing tomorrow. Be dressed for it, in other words. You're going to have to be walking out on a dock. Have your, I don't know what you wear to be walking on a dock, but it's not like a wedding dress or anything like that. All right, peace out.